Welcome to National Resource Center in Marine Science. I am Harilal B. Menon, Professor, Department of Marine Science, Goa University, and Coordinator NRC in Marine Science. You have been listening to various talks on oceanography delivered by different experts across the country. Among them, there was one talk on ocean observations, wherein he emphasized that there are two ways to observe the ocean. These are in situ observation and satellite based or remote sensing. In today's talk, I would explain you how the chlorophyll concentration in phytoplankton could be retrieved remotely, or how this could be sensed remotely, especially from coastal waters, which are highly optically complex in nature. The significance of knowledge about the chlorophyll distribution is that in the coastal waters, it's imminent to identify or to locate potential fishing zone, while in a global perspective, it's important for global climate. My talk of 1 hour has been divided into 4 different modules of 15 minutes each. In the first module, I would stress upon the fundamentals of remote sensing, and subsequently the intricacies or the details about the topic would be discussed. So let me begin my talk with a question of what is remote sensing. Remote sensing is a method by which the property of an object could be studied without having any physical contact with the object. Best example, I would say hypothetical example, is a cameraman taking the photograph, wherein without touching the body, he is getting the photograph. But this is hypothetical because he is not standing in a remote place to get the photograph. However, we have certain real life examples. One is estimating the depth of the ocean, and second one is studying the celestial bodies. So these are two typical examples, real examples. After having discussed this, let me try to explain you how we could achieve the goal of remote sensing, or how can we sense the object remotely. For this, we have to depend on electromagnetic radiation or solar radiation, which extends from cosmic ray, gamma ray, X-rays, UV, visible, IR, microwave, and radio waves. However, we cannot depend, or we cannot use all these rays for remote sensing. Rather, we would confine ourselves to visible, IR, and microwave, in the sense that if you have a satellite, and on the satellite, if you have 3 sensors operating in the visible, IR, and microwave, we would be able to get the information, or 3 different information of the same area through different sensors. What happens to these shortwave radiations and longwave radio waves? Cosmic ray, gamma ray, X-rays being shortwave radiations, they get scattered in the upper atmosphere, while UV radiations are coming inside, but then they are absorbed by ozone molecules in the stratosphere. And as you know that the inherent property of the EMR is that with the increase in wavelength, resolution decreases. Therefore, we don't use the radio waves for remote sensing activity. When you look at the advantage of remote sensing over the in situ is that this has got large repetitivity, one. Second thing is that it gives a large area of coverage, or it gives a bird's eye view. In scientific terminology, we can say synoptic coverage. Now, before going deep into the subject, it's important to know some of the basic laws which is important to understand remote sensing. There are basically 3 different laws: black body radiation, Wien's displacement law, and Stephens-Boltzmann's law. I would rather discuss Stephens-Boltzmann and Wien's displacement law. So let me explain that on the basis of this figure which is shown here. In this figure, what is shown is the intensity from different bodies having temperature ranging from 3000 to 6000 Kelvin. 6000 Kelvin represents sun. Now, if you look at the maximum energy coming out from a body of 6000 Kelvin, you would see that it is coming from this region. That means from the shortwave radiations. So the Stephens-Boltzmann law states that every body whose absolute temperature is above 0 Kelvin emit energy in a spectrum of wavelength which is proportional to fourth power of its absolute temperature. That's what is shown here in the right hand side. And Wien's displacement law states that with increase in temperature, the maximum energy is displaced to the shortwave radiations. That is typically seen from a body of 6000 Kelvin. Moreover, if you look at this, when the temperature decreases from 6000, 5000, 4000, 3000, you can see that the peak is displaced to long wave radiation. Another example is our Earth itself. The absolute temperature of Earth is 290 Kelvin and the maximum energy coming out is at 9.6 micrometer, which means that it's at IR radiation. As I mentioned earlier, the advantage of remote sensing over in situ is that it gives us synoptic coverage. I have given an example over here. This is information on land cover and use, habitat, landscapes and infrastructure. You can see that everything is available in one shot. And if the satellite covers the same area every second day or every other day, we would be able to get a time series variation of that region. And this is the the advantage of satellite or remote sensing technique over the in situ. And then multiple engagement by time series, as I already said, mapping and monitoring changes. Now it is time to understand that how or what are the different orbital characteristics of satellite. There are basically two different orbital characteristics. These are, first is polar orbiting satellites. These are launched at a height between 700 to 900 kilometers and it revolves around the Earth while Earth rotates from west to east. And these are the satellites which, generally we call those are the satellite used for retrieving the resource from the land and the ocean. And the second one, as I mentioned earlier, is Geostationary Satellite, which is launched at a height of 36,000 kilometers. The terminology itself suggests that it is geostationary. That means with respect to Earth, it is stationary. That's the meaning. But the speed of the Earth and the speed of the satellite is same. And India has a geostationary satellite wherein it always looks the Arabian Sea, Bay of Bengal and this region, so that it always acts like a security for us. For example, locating and monitoring the movement of cyclone and such other, the hazardous things are being informed through this geostationary satellite. Now, after having said this, now let us try to understand the various applications of remote sensing. In one way, I can say that natural resource management could be done or carried out by this remote sensing activity. In that, if I further say forestry, biodiversity, then deforestation, water source management, habitat analysis, environmental assessment, pest or disease outbreaks, impervious surface mapping, hydrology and mineral province, geomorphology, ocean biology, aerosol and climate. In this, today I would be concentrating on this ocean biology. We are launching satellite by spending crores of rupees. Okay, so it is necessary to know that the necessity and how the knowledge is disseminated and the societal applications. So if you look at this necessity, for example, in the coastal regions, we need this remote sensing or remote sensing activity or remote sensing methodology or remote sensing of the coastal region is required to protect environment, restore and maintain resources by monitoring coastal and inland waters, create and sustain a healthy and clean coastal water for societal benefit, advance the understanding of coastal processes for a better resource management, awareness of blue water among local population. Then further, coastal water climate and water quality, coastal weather in terms of outbreak of poisonous bloom. Very simple example is the trichodesmium bloom outbreaks in the coastal waters of Goa or in the west coast of India. This could be located and monitored by means of optical remote sensing. Then the quicker decision on usage of resources and improve forecasting isolated coastal events. Now, for all these things, knowledge dissemination is how to deliver accurate bioptical data for the coastal and inland waters from satellite measurements. Finally, the societal application is help in providing healthy coastal ecosystem, monitor isolated events affecting fishery. After having said this, let me bring your attention to the topic which we are concerned with, wherein first and foremost is I am trying to explain you the interaction of visible part of electromagnetic spectrum or the VIBGYOR with the waters of different optical domain. Let me show this like this. This is the inland water, which in remote sensing arena we call phase 2 waters. Inland water, when I allow VIBGYOR or the visible spectrum to interact with the inland water, I find that the color of the water is either red or brown or yellow, depending on what substance is prevailing in the water column. Or I would say that depending on what is the optically active constituents prevailing in that water column. Similarly, what I do is that I would allow the same VIBGYOR or the visible spectrum to interact with the coastal waters. We all know that coastal waters are 96% or 95% of the productivity is confined in the coastal waters. So you have more phytoplankton over there, and major optically active constituent there is phytoplankton. Therefore, when this visible, the light interact with the coastal water, the color is green. And I allow the same VIBGYOR or the visible spectrum to interact with the open ocean, and then I find that the color of the water is blue. Reason is that in the open ocean, certainly we have phytoplankton, but the concentrations are very, very, very less. So that means the controlling factor or the light is being controlled by water molecule. As a result, the photons associated with the blue light is getting scattered. So that is the reason why it is blue in color. Now, the most difficult part is this is what I would be discussing in the next some of the modules. From here, from this inland and this water coastal waters, how do we retrieve chlorophyll from satellite? Because one is any color it can be. So if you have different turbidity level, or I would use the word different turbidity level. Different turbidity level means different optically active constituents. So whichever is dominant, suppose you have inorganic suspended matter more in inland water, then the color will be different. So if you have more dissolved organic matter, the color is different. So therefore, from this water, how do we retrieve the chlorophyll from satellite data? Now let us try to understand. I have already said about optically active constituents. Depending on the optically active constituents, you have different color as far as the water body is concerned, I said. But let us now try to understand what are these optically active constituents. These are chlorophyll-A, total suspended matter, and colored dissolved organic matter. In fact, when I say total suspended matter, it involves both inorganic suspended matter and the fecal pellets of degradation of the phytoplankton. That is also there in TSM. And pseudomes is a part of the dissolved organic matter or the component of dissolved organic matter which interacts with the light. So these together can be called as biooptics. And ISM, inorganic suspended matter, has been again biooptics is a part of that. Now all these constituents together give the inherent optical property, which are A and BB. So the inherent optical property, that means the optical property inherent to that water body are absorption and backscattering. This doesn't, in fact, when I say inherent optical property, this doesn't depend on the incident light. Rather, it's the inherent characteristics. While we have apparent optical properties, these are reflectance, remote sensing reflectance, then attenuation of the downwelling irradiance KD and attenuation of the upwelling irradiance KU. Therefore, in case 1 water or the open ocean, we have chlorophyll and its accessory pigments as OACs along with the water molecule. So water molecule is another big component, another major component. And in case 2 waters, that means coastal and inland water, we have chlorophyll, TSM, ISM and pseudome as OAC along with the water molecule. Now, let me take you something very interesting. case 1 water, okay, when you look at this graph, in case 1 waters, you have, as I mentioned earlier, 2 optically active constituents. That means the chlorophyll, of course, water molecule cannot be considered, but let me, for convenient, let me say that you have chlorophyll along with the water molecule. So if you look at the spectral absorption of chlorophyll, you would see that there is a primary peak at 443 nm and secondary at 663 nm. And at the green part, 555 nm, you have least absorption. So you have high absorption, so the absorption increases, there is a primary here, and then exponentially decreases, and there is a minimum absorption over here. And along with that, if you look at the water molecule, minimum absorption here, and it exponentially increasing when you go to the longer wavelength. This means that all that energy associated between 400 to 500 nm have been exclusively used by phytoplankton, in the sense that when the satellite goes over an area, over an let's say coastal water, where you have high chlorophyll and less chlorophyll, let us say, over the high chlorophyll, the blue band of the satellite sensor would be getting the less information content, while the green will be more. That means when, depending on the spatial heterogeneity of the chlorophyll concentration, you would find that there is an inverse relation between blue band and the green band. This has been made use to develop an algorithm called a band ratio algorithm, and for the first time this has been developed by Gordon et al. In the year 1981. So wherein chlorophyll is equal to A into ratio between blue band to the green band into constant, and this equation is basically derived statistically, in the sense that you have the band ratio on x-axis, and the y-axis you have the chlorophyll derived from the water sample, and this is being derived. And to get this, what we normally do is that we have a ship cruise in concurrent with the satellite pass, we'll have the measurement, and that is being used for developing this particular band ratio algorithm. But when you look at the case 2 waters, you can see that along with the chlorophyll and water molecule, you have CDOM and you also have TSM. So if you look at the spectral absorption, the energy that is supposed to be used by chlorophyll have been shared by TSM and CDOM. Therefore, we cannot use any band ratio algorithm here. And this is the last slide of this module. In the next module, I would take you the spectral variability of RRS at different water column, and that would give an idea about the optical complexity prevailing in the coastal and inland waters. Thank you.